Hi everyone, welcome to this machine learning and MFG games webinar. So today we're very happy to have Gökçe Dayanıklı, who is from UIUC in the statistics department after a PhD in Princeton and postdoc at Columbia University. So thanks a lot for accepting to present, Gökçe, and the floor is yours.
Thank you so much, Matthew, and all the other organizers for inviting me. It's a great pleasure. So today I'm going to talk about utilizing deep learning and game theory to find the optimal policies for societies. So the deep learning part is related to the machine learning and the game theory part for the Minfield game. So I think it's a good fit for the webinar. So this is a joint work with Matthew Laurier. So let me get these tools up. So I'm going to start with the motivation. I'm very interested in basically policy making problems. So from there, I was interested in the following question: how can we design the optimal policies or incentives in order to get the best outcomes when we interact with many rational agents who prioritize their own? Because in public policy type of applications, we generally deal with a society with people who has their own objectives. So this requires us to do some kind of game theory for the large groups. So some of the examples for these type of problems can be, for example, finding the optimal carbon tax levels for a large number of electricity producers. So here, for example, the electricity producers can be in a cooperative or non-cooperative way, and we can be a regulator or a principal. This would be the government trying to set the carbon tax levels, and the electricity producers would basically respond back with their average supply, which is at the end going to determine the price of the electricity. Or we can have, for example, optimal advertisement decisions applications for companies interacting with consumers. For example, we can have either one company or we can have two companies, and we can look at their advertisement competition when they are interacting with a basically large group of consumers who are choosing which product to buy from which company. And another one can be, especially during the COVID, this was a higher interest, basically finding the optimal policies to mitigate an epidemic. And I'm going to discuss one example at the end related to that. Basically, the principle again can be a government, and this principle can choose social distancing policies they want to set. But as we saw, during the corona, people are not responding exactly according to these policies. They choose according to their own taste. For example, even if there was a mask mandate, there were some protests for people who didn't want to wear masks. So we want to take into account this type of behavior of the agents where we can't directly control them. Instead, they are responding according to their own objectives. So let me give the outline of the talk. First, for the people who are not very into the continuous time models, I'm going to give the review of the stochastic optimal control for only one agent and how we can solve it with deep learning. As far as I remember, in this webinar, there is more a discrete time setup. So I wanted to start from the building block of continuous time stochastic optimal control problem, and then from there we are going to build it. Then what we are going to look at is basically large populations and how we can find the Nash equilibrium. Here, very, very briefly, I'm going to mention the Minfield games, but I assume that many people in this webinar already know this, but we can just give the setup in the continuous time. Then we are going to look at how we can use deep learning to solve Minfield games. Then what we are going to do is a Stackelberg equilibrium. We are going to look at its definition and how it is different than Nash equilibrium, because sometimes it can be confused. Then we are going to discuss how we can basically find the optimal policies for large populations under the notion of Stackelberg-Minfield games. Then we are going to show that the Stackelberg-Minfield games is actually a bi-level problem, which is going to be inefficient to solve. So in order to efficiently solve it numerically, we are going to try to write it as a single level problem. And after that, we are going to give the deep learning methods for this and look at some examples. So let's start with the review of the stochastic optimal control problems. As I said, this one we only have one agent. We don't have the population for now. This agent is trying to minimize her cost, maximize her rewards, and she's trying to choose her controls between the time 0 and the terminal time t. In this talk, I'm going to talk about finite horizon problems. By the way, if you want to stop me and if you ask questions, please let me know, because sometimes I don't see people, so you can unmute yourself. So in this setup, for example, this person is going to have state that is going to be denoted with xt, control alpha t, and some objectives. And let's assume that we have an example. We have an employee Rebecca, and like she's working in a company, and she's going to choose her efforts level. And this efforts level is going to affect her value of the project. And in this case, basically, the state of the Rebecca is going to be the value of the project she's working on at time t, and the control is going to be the effort level at time t, and the objectives, for example, can be the utility from the project value. Maybe they are getting paid according to that, and also there's going to be a cost for putting too much effort. So in this case, we can basically model this problem as follows. So what we can have is that we are going to have a minimization. So here we are going to write the costs. We are going to have some cost from having a lot of effort applied. We are going to have some utility where this u is a utility function from the project value, and we can have a terminal cost similarly. And the value of the project is going to depend on the effort of this Rebecca. And basically, as you can see, the control is going to be on drift. And for now, like I just get a constant drift, and this is the Brownian motion. So I think this setup is very familiar with many people, but I just wanted to introduce anyway, because we are going to build on this one. So when we have this problem, what we do is generally we wrote it in the generalized form. We write the running cost generally with f, and it is going to depend on time, the state of the agent Rebecca, and the control of the agent Rebecca. So this is the value of the project and the effort that she's putting in. And the terminal cost is generally denoted with G, and I'm going to employ this notation throughout this talk. And for the drift, I'm going to use B. Previously, we said that the drift was only alpha t, but actually it can depend on time, state, etc. And the initial position is going to be generally a random variable. So when we have, right now, like we have only one agent, so there are no interactions with other agents, but when we have interacting agents, when we have large number of agents, especially, we need to use game theoretical tools, and we are going to discuss about this, but first I'm going to introduce a little bit how we can use deep learning to solve this stochastic optimal control problem. So let's look at this. What we can do is that we can, for example, use the fact that neural networks actually can approximate functions. So what we have here is that, as you know, that we can input an X in neural network, and these W's and theta's are basically weights, and sigmas are the activation functions. By the way, sorry for my very bad handwriting, like it's sometimes hard to read. But at the end, with this input X, we are going to have some output that depends on the activation functions, and more importantly, the parameters that we denote with theta. And this is going to be a function f theta x. It is going to depend on the input and the parameters that we choose. And what neural networks does is basically choosing these parameters according to some kind of a goal. So what we can do is that if we want to approximate a function, basically we can use this idea of neural networks creating a function of x that is parameterized with theta, and we can try to basically set or aim to approximate the function fx. So in this case, basically what we are going to do is that we can build neural networks. It is going to basically output an f theta x, and we are going to train it over the parameters theta by using the objective of this f theta x is close enough to fx that we want to approximate. So this is the idea of basically using neural networks as function approximators, and we are going to use this idea to solve the Stackelberg mean field games. So let's look at how we can do this in the stochastic optimal control problem. What we are going to do is that we are going to assume that the control of a t is a function of time and the current state. So we can denote it with Morphy, txt, and then we can discretize the time, because like we are dealing with a numerical algorithm, so we need to discretize the time and write the discretized version for the stochastic differential equation we have. And we need to write a discretized form for the continuous time cost we have. Then what we are going to do is that we are going to initialize the state x0 according to the distribution, the initial distribution, and we are going to simulate the trajectories of x by using this discretized stochastic differential equation. Then this is here for the control, we are going to use the neural network outputs. So basically at time x0, our neural network is going to take 0 and x0 here, and it is going to return a control for us. And we are going to put it here, and we are going to put x0 here and 0 here. We are going to find b. Then we are going to basically plugging in the randomness here and delta t here, and we are going to find xt1. And in this way, basically, we are able to find the whole trajectory of the x over the whole time sequence, and also the control. Then we can plug it in the cost at the same time. And our aim is basically trying to minimize this cost, because in the stochastic optimal control, the aim of the person was to minimize this cost. So our neural network is basically trained over the parameters theta in order to minimize this cost. So basically, we want to use this idea. Do you have any questions for now? I think that's good. Okay. So let's start with the game theoretical part and start with the Nash equilibrium. Here, I'm going to be a little bit fast, because I think everyone already knows the Nash equilibrium part. So what we want to do is that now we had one person only, but we want to look at a big population, and we want to look at basically non-cooperative agents. And in this case, we want to look for the Nash equilibrium in the population. But our problems are dynamic, stochastic. We have large number of agents, and we have continuous action space generally. And in this case, basically, it is pretty hard to find the Nash equilibrium. And as you know, we can use some approximations like the mean field approximations. So what we are going to do is exactly this. We are going to directly look for the mean field game. So as you know, like what we assume is that we have infinitely many people in the population for the mean field games. They are going to be identical and infinitesimal. This assumption can be basically extended. For example, you can use, and also the next assumption can be also extended, which is agents interact symmetrically. For example, you can have some kind of a network structure, and you can look at graphon games. But anyway, in this one, for now, we are looking at the most basic setup, where we assume that the agents are identical infinitesimal. They interact symmetrically through the mean field interactions. And in the talk, I'm talking about the case where they are interacting through the mean field interactions of the population state, but actually all of the things can be extended to the extended mean field games, where the interactions are also through the control. So what we are going to do is that following, we are not going to look at the finite player setup at all. We are directly going to look at the mean field game setup. We are going to look directly the representative agents model and her interactions with the distribution. So let's look at the mathematical formulation of the mean field game. The reason I wanted to introduce the stochastic optimal control was because of the reason that we are using the same notation. So as you can see that now we are assuming that there's a large number of agents, and we are approximating this the year game with a mean field game. And now I'm basically introducing the problem of the representative agent. This representative agent wants to minimize a cost, and it has a running cost part and a terminal cost part. And it's using a control, but it is also facing a population with a state distribution mu. As you can see, different than the stochastic optimal control problem, we have the distribution now here. And the agent state is going to get affected by the mu too, and also her own control and her own state. So here we define the mean field game Nash equilibrium as follows. What we have is that we need to have for this representative agent, alpha needs to be the best response, or in other words, it needs to minimize the cost of the representative agent given the population distribution. So we fix the population, we find the best response of our agent, but then we need to find the Nash equilibrium, which means that the distribution of the representative agent X should be actually the distribution that we fixed at the beginning. Since everyone is identical, we basically fix a population, we find the best response, and since everyone is identical, we assume that everyone should behave the same. So the population distribution that we set at the beginning should be equal to the distribution of the representative agent state. So this is basically the mean field Nash equilibrium, where we first do optimization, then the fixed point step. And then what we can do is that in the continuous time version, basically we can characterize it with a forward-backward stochastic differential equation system. So here, basically, I included a very small example just for how the forward-backward stochastic differential equations work. So let me show you. So again, instead of one agent, we have a large population. So let's assume that everyone is minimizing their cost and choosing their own effort levels, like the model of Rebecca. And their project value, each individual's project value is going to depend on the average project value somehow. So this is I'm not going to claim that this is realistic model, etc. I just wanted to put it as an example. So as before, like we have the cost of effort here and some utility from the individual project's value xt, and the agents, the representative player also have some terminal utility that I denoted with G to differentiate from this U. Then for the drift, we have the effort affecting the value of the project, but I also say that the project value dynamics depend on the average project value, so I added this here. So this is very like little mean field interaction. As you can see, I didn't put it in the cost, etc. So like it is not like fully mean field in cost and drift, only in drift, but for showing the basically forward-backward stochastic differential equation, this is not a problem. So in this case, for example, we can say that the Nash equilibrium control is given like this. And this X, Y, and Z trajectories that you can see is here. X is the value of the project, and Y is going to be an adjoint process that is going to characterize the basically the value function, and they are going to be determined by a forward-backward stochastic differential equation. Basically, forward one is the state dynamics at the equilibrium, and backwards one is the value of the value function of the representative agent. And as you can see, the first one is starting from the initial point, and the last one is starting from the terminal point. And since this adjoint process YT is characterizing the value function, as you can see at the terminal time, it is going to be equal to the terminal cost of the representative agent. So this is, for example, a very simple model. The existence and uniqueness can be like discussed, etc., but this was only for basically showing how this FBSD can be written. So let's now look at how we can solve these mean field games by using deep learning. Basically, what we are going to do is that we are first characterize our equilibrium with an FBSD, as I showed. Then what we are going to do is that we are directly going to focus on solving this FBSD. When I say FBSD, I mean forward-backward stochastic differential equation. So the forward-backward stochastic differential equation that I showed in the general model notation can be written like this. As I said, this is the state dynamics, and I write the differential equations in the integral form. Since this was a forward equation, it starts from 0 and it goes to t. And as you can see here, I'm using the equilibrium control alpha hat. So this is going to depend on the x and z, and it is going to couple with the backward equation for the adjoint process YT. As I said, this yt is going to characterize the value function. So again, I wrote it in the integral form. So this is the terminal condition, which is the terminal cost of the agent, and it starts from terminal t and goes to the time t. So here, the challenges of these things, they are coupled. As I say, this alpha hat s is going to depend on t, x, and z, and they are going to be coupled with each other. They are making Villasov type equations, which means that the law of xs is also in these equations because mu s is going to be the law of xs. So as I said, the important thing here is that the backward dynamics represent the value function because we are going to use this fact in the Steckelberg mean field game. So this is the equation system that we want to solve. So let's see how we can use this like neural network idea to solve this problem. So what we are going to do is first, these are like one of coupled equations, and one of them is going moving forward in time. The other one is moving backward in time, but we want to discretize them and we want to solve them basically simultaneously. In order to do this, we need to start from a time together, and we need to, since they are coupled, we need to simulate them together. So what we can do is that for the backward equation, we can try to use some kind of shooting method, which means that instead of like starting from a yt that we know and going back and finding some y0s, we need to choose some initial position y0, and we need to go to a yt and see how much we are away from this yt. So this is going to be the shooting method. So in order to do this, what we are going to do is that we are going to write this yt in the following form. As you can see now, I'm starting from an initial position, and I'm starting from 0 to t, and we change the signs here. And by choosing y0 and this z here, I am going to basically end up at a yt. And I'm going to try to see whether this is close enough to the terminal condition we should have. Do you have any questions for now for this idea? Okay, so let me continue a little bit more. And if you have any questions, we can discuss further. So here, basically, we write our now forward stochastic differential equations because I'm writing this forward too. And I'm trying to shoot the terminal condition that we need to have. So what we do is that, again, we discretize the time as before, but now we have a distribution, mu s. So we need to basically simulate populations this time. We simulate a population of size n, we are going to use their empirical distribution mu n instead of this mu s. So
Gökçe?
then what, yeah.
Sorry to interrupt. I think there is a question in the chat about what is Z.
Okay.
So what is that in the BSD?
Yeah, that is this thing in front of the Brownian motion, and basically this is the approach where we are characterizing the value function. It is a little bit different than stochastic Pontryagin principle. So what we are going to do is that we are going to have a Hamiltonian to find the equilibrium control. We need to minimize this Hamiltonian, and in the Hamiltonian, the adjoint process is going to be ZT over sigma actually, and it comes from there. And then like the t is also in front of this Brownian motion. So it is going to be the process that we are going to be plugging in the Hamiltonian. So it is a little bit different than the Pontryagin principle. And the reason why we are using this is we want to characterize the value function because we are going to use this fact in the Steckelberg mean field game. Is it clear? I hope so. Okay.
Yeah,
okay, maybe
so. Yeah.
he can ask again.
Okay.
Yeah. Okay, so the last point is basically now we need to approximate controls. But what are the controls here? In the stochastic optimal control problem, it was a little bit more clear. But in this one, we are trying to solve this FBST for x, y, z, right? And we know the initial of x0, and then we can simulate it with this differential equation when it is like time discretized. For the y, we don't know the initial y0. We know the terminal condition for that. So we need to choose this thing. And we also don't know what this is, and we need to learn this. So what we do is that we are basically approximating functions for y0 and zt. For y0, it's a function of the initial state, and for zt, it is a function of the current time t and the xt. And then what we do is that we basically simulate the trajectories of xt, yt, and zt. Then at the end, we are going to be able to calculate this error. And our aim is basically minimizing this error. So what we try to do is that we are trying to minimize this distance to the yt that we need to end up. Okay, so is it clear, hopefully? So here, basically, if you want to look at a finite state application, the epidemics paper that I'm going to mention at the end has the finite state application for this. And if you're interested in like network interactions, we have a graphon game application. Again, it was coming from the like motivation of epidemics control. And the idea there was during Corona, people weren't identical. Some people were getting affected a lot, and some people were not getting affected at all. So we needed to have some heterogeneities and unsymmetric interactions. So if you're interested in graphon game application of this type of solution, of course, things are going to be a little bit different, but similar flavor, basically. You can check the other paper too. So now let's go to the Stackelberg equilibrium and introduce the Stackelberg mean field games finally. The good thing is now we know a lot of like background information, how we can solve especially mean field games and how we can do this shooting methods. I think the important part in the Stackelberg equilibrium and the Stackelberg mean field games is going to be first to introduce the Stackelberg equilibrium, then how we can basically rewrite the Stackelberg mean field game after introducing it. But then the deep learning approach is going to be similar. So let's look at what is a Stackelberg equilibrium for the people who may not be familiar. So as I said, that our main aim is to design optimal policies and incentives in order to get the best outcomes when we are interacting with a large population of non-cooperative agents. So let's assume that we have the principal and one follower. This is the classic Stackelberg equilibrium. So we don't have the full population. In the classic Stackelberg equilibrium, this one leader, or we call it a principle in this talk, is going to choose some incentives or policies, we can call them, and the follower or the agent gives the best response to these incentives. And then the leader is going to optimize incentives by taking into account the best response reaction of the follower. This is different than Nash equilibrium, because in Nash equilibrium, both of the agents give their best responses, then we do a fixed point on this. But in this one, actually, first the agent gives a best response, then by plugging it in the problem of leader, the leader is going to do an optimization. So in our setup, as I was mentioning for some time, we have a population. So instead of one agent, given their best response to the incentive, we are going to assume that the population is going to respond with a Nash equilibrium given the incentives of the principal. So for the Nash equilibrium in the population, we are going to approximate it with the mean field game, and we just introduced it. So like in the deep learning methods are going to be similar to that part. So let's look at the Stackelberg mean field game model setup. Let me give you some like related references first. Some of them, for example, in the more contract theory model type of like applications, we have Eli, Mastroianni, and Poissonnier in the continuous state space form. These are all continuous time, by the way. And we have Carmela and Wang in the finite state space part. The important thing here is that the year form of the model is spatial. I'm not sure whether I'm going to have time on this today a lot, but thanks to this model form, they are able to write the year problem as a single level without getting into too much form, but it is a little bit restrictive. And for the numerical approaches, this is the epidemics paper that I mentioned. Again, we had this spatial form of the model that which was helping us. And there's also a paper of Campbell et al. And they are also solving a Stackelberg mean field game problem. But in the year setup, basically, I'm going to show that this Stackelberg mean field game problem is a bi-level problem. They are basically solving numerically by setting an incentive for the population, then the population finds an equilibrium, then they set another incentive and they try to optimize over this incentive. So this is what we are trying to improve on. We don't want to do this bi-level numerical approach. We want to somehow like solve it in one single run. So we want to write our model as a single level problem. So if you want to look at especially the theoretical details that I'm not going to go into detail today that much, you can check the paper. It is on arXiv right now. Okay, so our agent population, I'm going to be quick here because we already introduced the mean field game. I'm just going to show you what's going to change. So let's assume that our principle is setting some incentives. Let's assume that they are time-dependent policies. So lambda is going to be a function of time t. And I'm going to denote it with lambda t. And this can be extended, but for now, let's assume that it is just a function of time. So then the mean field game model for the representative player is going to be similar to before with the addition of this principle's incentives. As you can see, the principle is affecting the agent in the cost function and also the drift. So different than before, yeah, we have these orange parts, and but at the end we can still basically characterize the mean field Nash equilibrium with a forward-backward stochastic differential equation given this lambda t. So that part is still valid. Then for the principle, the equilibrium, etc., is going to be characterized like this. So we are good there. But now, we can go to the principles part. For the principle, we have their own cost. So as you can see, I denoted it with F0 and G0. It is different from the agent's population. So here, what they are going to have is that they are going to get affected by the agents through the mean field distribution, basically. For example, if this is an epidemics application, the principal may know the proportion of infected people. So this is our motivation. And also their cost is going to depend on their own incentives, lambda t and lambda big T. So in this case, the principal's problem is not just minimizing this. It should be careful because it should assume that given any incentive lambda, the agent population is responding with a mean field Nash equilibrium. So this part is important. This basically after setting lambda, the population is going to respond with a control, basic equilibrium control that is getting affected by lambda, an equilibrium mean field that is getting affected by lambda. So this is not just optimizing over these things. As you can see, these mu's are also depending on lambda. So this function is going to be very complex to optimize over lambda. Okay, so any questions for the setup? So at the end, our full problem as follows. We have a minimization for the principal. It has the running cost and the terminal cost parts. Then for the equilibrium in the population, as I introduced before, we have a forward-backward stochastic differential equation system. So for the forward part, again, it is the state of the representative agent in the population, and the value function, the backward one is characterizing the value function of the representative agent. So as you can see, we have the terminal cost of the agent here. This is a bi-level problem. Why? As I was a little bit introducing in the references, we have this principle at the top, and this principle is going to choose some lambda. Then after choosing some lambda, the equilibrium needs to be found by solving a forward-backward stochastic differential equation system. Then we need to plug this basically mean field back into the objective of the principle. Then they are going to, again, optimize over their lambda. So this creates a bi-level problem, basically, that includes the optimization and an equilibrium at the second level. So how can we rewrite this problem to end up with a single level problem? Because as I said, in our motivation in this paper that I'm introducing now is basically writing this problem in a different way so we can try to solve it numerically more efficiently. So let's look at the problem we have. We have the following objective. This is the principal's objective. Then we have some forward-backward stochastic differential equations. As we did before, what we need to do is that at some point we are going to discretize the time and we want to solve these things together. So as I introduced, as similar to what I introduced for the shooting method, we are going to do something in the same sense. We are going to basically rewrite this backward equation forward in time. And as you can see, again, we have y0 z s. It is very similar to what we introduced with the addition of lambdas. Then we have this constraint, right? Previously, in order to solve the mean field game, what we were trying to do is that basically we were trying to minimize the error. That was our error. But now, like we have this as a constraint, and if this is not satisfied, basically it means that the Nash equilibrium in the population is not solved. So we have to satisfy this thing. And then another thing that's important is that now this is a problem where we have an objective, we have some dynamics for the trajectories, and we have some constraints, and our controls are previously for the principal we had lambda, but now we are also controlling the initial position of y0 and this randomness in front of the coefficient in front of the randomness, and we are simulating x, y, and z. And thanks to this x, we are able to find the empirical distribution. So this mu is going to come from the empirical distribution of x. So by keeping this in our mind, let's see how we can do this, rewrite this problem more, and we can apply this idea. So what we are going to do is that it is very hard to solve the constraint optimization problems. So we are going to relax this problem with an introduction of the penalization. So we are going to take this objective and we are going to plug it in the objective of the principal as a penalty. So as you can see, for the principal's objective, we have this part. And also we have some penalty for not finding the Nash equilibrium. And in order to find the full Stackelberg Nash equilibrium, what we need to have is that we need to have this thing going to 0. So here, P is a penalty function. If this constraint is satisfied, it's going to be 0. Otherwise, it is going to be positive. And nu is a coefficient in front of the basically penalty. And this nu can be chosen by basically the person who is simulating. So at the end, our rewritten penalized problem is going to become this. We have some objective and we have some forward stochastic differential equation problems. This is actually very similar to stochastic optimal control problems, but now like we need to basically simulate a population of X and Y, and we need to basically find this distribution empirically by taking the distribution of X. But we are going to be trying to minimize this thing. And if we can show that this penalty goes to 0, then it means that Nash equilibrium is simultaneously solved with the Stackelberg equilibrium. So this means that Stackelberg mean field game is solved. So this is a single level problem because we choose lambda, y0, and z, and we can simulate and find a cost. Then we are going to optimize basically, if we are plugging in neural network parameters, we are going to optimize over the neural network parameters. So this is going to be more efficiently solved. So let's look at the deep learning idea here. What we are going to do is that we are going to use the neural networks to parameterize the new controls. Lambda was the principal's incentive. Z was the coefficient in front of the randomness in the previous backward equation of the FBSD. And Y0 is the initial point that we are choosing to simulate our previous backward equation forward in time. Then we are going to Monte Carlo simulate the trajectories of xt, yt, and also zt, actually, by using the time discretized forward stochastic differential equations. And for the distribution that we have here, this is basically the distribution of x. We are going to use the empirical distribution of state x. So we need to basically simulate a population of n, and all these agents are going to have an x, have an y, and it's going to have an z. Then what we are going to do is that we are going to minimize over the neural network parameters of these functions, the time discretized and penalized cost of the principal. So as before, we are going to time discretize this, and this is the penalty part. So our aim is basically trying to minimize this thing. So the important thing here, as I said, we need to, on the theory side, we need to show that the solution of this problem is converging to the solution of the original Stackelberg mean field game problem. And how we can show this is that we need to show that this term is going to 0, because if this condition is not matched, it means that the Nash equilibrium is not solved. So I didn't want to include too much theory for this talk, but if you're interested in what we show in the paper is that the solution of the parameterized and the penalized problem is going to converge to the solution of the original Stackelberg mean field game problem as this nu goes to infinity. This looks like very intuitive, but the proof was a little bit complicated, so it is still required a little bit work. Okay, so do you have any questions for maybe the algorithm, how we can use the deep learning to solve Stackelberg mean field games, etc.? Okay, then I'll start with the numerical results. The first one is going to be a little bit toy model, because we want to compare it with a model that we have some kind of a semi-explicit solution. So let's look at the first example, which is a systemic risk model with the regulators. In systemic risk, what I mean is that systemic risk of banks. So what we are going to have for the agent population is that we are going to have a large number of banks. And these banks are going to control their lending and borrowing amount from central bank. They don't lend and borrow from each other. And basically, they are going to have as their state their cash reserve. So this mean field game model for the banks, this part is introduced in Karmanoff and Son. And what we do here is that, and they have an explicit solution, which is very helpful. What we do here is that we add a principle that kind of follows their intuition. And we are trying to basically solve the Stackelberg mean field game between them. But we are adding a very naive principle to have some kind of an explicit solution, or how, like what we should expect basically, so we can see whether our numerical approach is similar to what is expected. So what we do is that for the principle, they are going to propose an incentive that is time dependent, as I said, and they are going to have the following objective. This lambda t aim is an exogenous level that is set, and our principle is going to be try to be close to this aimed level. And also this this t is a default value. This principle is also going to try to minimize the bank's probability of defaulting. As you see, when the cash reserve of the bank is smaller than d, it means that they are defaulting, and they are trying to minimize this probability. The important thing here is that if this coefficient gamma is 0, then what we are going to have is that just this part. And as you can see that we don't have an interaction directly with the mean field. Like the agents are not affecting the objective of the principle directly. So what we are going to have is that lambda t needs to be equal to lambda t a. So given if this gamma is 0, we kind of expect this lambda t to be equal to lambda t aim, and given this lambda t equal to lambda t aim, we need to have the mean field game to be solved. And the other thing is that if this gamma is not equal to 0, we are expecting probably this may differ, because now we have some kind of a trade-off, and the principle needs to take that into account. So for the banks, as I said, they are controlling their lending and borrowing amounts, and this is the cash reserve, and they are interacting with other banks through the average cash reserves. For example, they want to be around the same level with them, and they are interacting with the principle, as you can see, through this lambda. So let's look at the first result. The first result, as you can see, gamma has 0. So what we expect is that we are expecting the lambda that the principal is choosing, the incentive, should be equal to the lambda aim. And as you can see here, in this one, I don't know, in this one, lambda aim is lambda that is chosen by the principal is very close to lambda aim as we expected. But another important thing here is that this plot, this is the penalty plot that shows that penalty that shows that the Nash equilibrium is satisfied or not, is going to 0 or not. And as you can see, it is going to 0. This means that we are also solving for Nash equilibrium. So we can conclude that this approach is able to find the Stackelberg-Nash equilibrium in this setup. Then we can look at a case where gamma is not 0 anymore, as we expected. Now lambda is not equal to lambda aim because they have a trade-off. But again, the important thing is the penalty to show whether Nash equilibrium is simultaneously solved. And as you can see, it goes to 0, and we can say that we are indeed finding the Stackelberg mean-field game equilibrium. So before concluding, I'm going to introduce a small, small application from our previous paper. This is actually a finite state model, but similar ideas can be used, and the model is interesting. So what we have here is that we want to mitigate the epidemics, and for the agent population, their states can be susceptible, infected, and recovered. And from susceptible to infected, they are basically transitioning depending on how much they socialize through alpha and how much every other infected person on average socialize. So now they have a mean field interaction, and actually they have an extended mean field interaction because, as you can see, that the interactions are coming through the joint distribution of state and the control in this one. And for the principal, they are going to choose the social distancing measures and the stimulus payment at the end. This was actually related to that spatial model form that we wanted to extend previously. And their objectives are basically following the recommendations from healthcare professionals and flattening the curve. This was basically what it meant, is like they wanted to minimize the proportion of infected at each time step. So then we can write the agents model as follows. They have this is the policy set for the susceptible player by the principal. This is for the infected, this is for the recovered. And basically they want to be close to these policies set by the principal. And for the infected people, they have some kind of a treatment cost. And at the end, as you can see that they are getting some kind of a stimulus check. So this is going to be shown with a negative because it's some kind of a utility. And for the principal, as I say, they are trying to flatten the curve, and by trying to minimize the proportion of infected, this is the mean field interaction. And then they are trying to basically be close to the recommended policies, that these are going to be set, the bar ones, and these are going to be chosen by the principal. And what we show is that first we solve the mean field game by fixing the principle as it is, and we are looking at the case where the principals are doing some kind of restrictive social distancing policies on day 40. So when this dashed lines, the blue ones are for susceptible and the orange one is for the infected, is the policy of the principal. And when it is lower, it means that they are restricting the social distancing policies. As you can see, on day 40, they are restricting. And these top ones are the explicit solutions we have, and these ones are our numerical solutions results. And as you can see, these solid ones are the Nash equilibrium responses. And what we can see is that our numerical approach is very good at mimicking the explicit solution. And the other one is that in this one now we are solving the Stackelberg mean field game, not just mean field game. And we are looking at a higher dimensional problem where we add also the state exposed and state diseased. So our people are first changing to exposed, then after some time from exposed to infected, they jump. And then what we are going to do is that we are going to look at our results. And what we see, now we are solving the Stackelberg mean field game. So the policies are not exogenous decided. They are coming from the solution. as you can see that the policy set for the susceptible people with the dashed blue line is just a little bit below 1, which was the maximum level they can have. So this means that the government is putting just a little bit restrictions to the susceptible people. Maybe they are requiring them to wear a mask in the basically crowded places. But our Nash equilibrium response, as you can see with the solid blue line, is much more restrictive than this, which means that our rational people are basically trying to are basically thinking that these restrictions are not strong enough, and they are restricting their behavior a little bit further. So like I always give this example when I was in Princeton during Corona. What we saw is that we didn't have the mask mandate outside. So but people were still wearing masks even outside, because I think they were thinking they weren't safe enough and it was very dangerous. So they were restricting their behavior further than the policies said. This is actually a little bit interesting, because intuitively what we think is that people don't want to follow the policies. They just want to they just want to have more relaxed things. But I think when health is in stake, I think they want to be more restrictive to protect themselves further. So this was one of the results that was interesting for us. And another thing is that here, basically, we are comparing our Stackelberg-Minfield game result, cumulative infected people density, to the case where we don't have any policy set and or people are not restricting their behavior too. This no policies version is the dashed one that we call free spread, and the Stackelberg-Minfield game result is the solid one, and this comes from our solutions. And as we can see that we are able to decrease the proportion of infected. So we are saying that, finding optimal policies is important. So here I'm going to basically conclude. What we did is that we discussed a little bit deep learning approaches, starting from stochastic optimal control. We built towards Minfield games and towards Stackelberg-Minfield games. Then we discussed some, very briefly, what was the theorem we ended up. And we introduced some basically examples and how our deep Stackelberg-Minfield game algorithm works on these examples. So if you have any questions, please let me know.
Okay, thanks a lot, Gökçe, for the nice talk.
Thank you, me too.
Are there some questions? Feel free to unmute yourself if you want to ask something.
I guess there's a question from Alex, but I have one afterward if you want to take Alex's question first.
Okay, yeah, there is a question
slides.
about sharing the slides.
Sure.
Yeah, sure. If you don't mind.
Sorry.
Should I send it to you?
Yeah,
maybe
you can
send...
send it to me. I can put them on
Sure.
the website. Yeah, so
Yeah.
the slides and the recordings will be on the website later.
Yeah, that's a good question. It's not a library and package. Basically we have the GitHub, but our policy is generally sharing making the GitHub public after publishing the paper, and this is under revision right now. So hopefully after that we can make the GitHub library public. But for the other epidemics one, that we don't have this one level approach in that one, but for the epidemics one we have the GitHub libraries public. Maybe I can send them. Yeah, me too has them too, so can send it maybe.
Yeah, feel free to contact us, maybe
Gökçe
or me after, and we can share.
Yeah, the epidemics and the graphon one is also public, so we can share those.
Mm-hmm. Okay, nice. I think you had a question. Yeah, Bora, yeah.
So I guess two. One of them is really quick. The first was, when you say bi-level, do you mean kind of inner loop, outer loop, nested loop structure? And
exactly.
you're trying to
it's 2 for loops basically. If you think about coding. Yeah, we want to get rid of it because it's a little bit inefficient.
Yeah, of course. Okay, that's great. The second question, I think it was around slide 26 or 29, somewhere in that range. There was a bold P penalty term, and I was hoping that maybe you could explain that a little bit. I guess.
Sure.
I'd love to hear.
Here. This P, you can basically choose it. And one thing it needed to be is that it needed to be Lipschitz. So that was for the theory. But what's important is that it needs to be 0 when the constraint is matched. It's just the penalty term. And it needs to be positive when it is not matched. And our constraint is basically this yt is equal to g. So as long as this yt is equal to g, indeed, this penalty needs to be 0. If they are differing, then it needs to be positive. This is the important thing. But in the problems, in the algorithm, what we did is that we took it to square. I know that it is a local Lipschitz, so what we do is that we do square, then actually linear after some parts, but we take that square part very big. So like in the algorithm, if you just use square, it's still fine. Yeah. That's good.
Okay.
I guess. Okay.
Yeah. Is there? Oh yeah.
I think there's a question. Yeah.
Yeah. I think you're muted. Do you want to?
Yeah.
Hong, do you want to unmute yourself or?
Yeah, sorry. I have a question about page 26.
Is it? Sorry, let me see. Oh, sure.
The previous one, yeah. Yeah. Okay. So you said it's a Stackelberg equilibrium because for the control problem of the principal, the distribution depends on lambda. So whenever lambda moves, mu moves with lambda too, right?
Yes.
So it doesn't mean that if I don't do that, if I don't put the lambda there, I still have a gain problem, but it's like not a Stackelberg, but a Nash.
Yeah, you can have also like a Nash one. For example, there is a major minor midfield games where they find a Nash equilibrium between a major player and a like a minor player population. So there are versions with a Nash equilibrium too. But indeed, like the fact that this mu is going to be plugged after we inject the lambda in the equilibrium creates the Stackelberg equilibrium. So in Nash equilibrium case, what would happen is that you would assume that this is exogenous. You would basically find the optimal control lambda here. Then you would assume that lambda is exogenous. You would find the equilibrium here. Then you would do a fixed point between the mu and the lambda because they're going to be each other's functions. Then you would do a fixed point. Then it would be, I believe, Nash equilibrium.
Yeah. So so here the distribution. As you explained in your first model on the banking, the distribution goes into the drift, but not the cost function of the principal. I imagine that if you have a distribution in the cost function of the principal, it's going to be a very complicated problem because if you try to write down the Hamiltonian, then the Hamiltonian with some super in from lambda, but then there's a distribution inside the Hamiltonian moving with lambda. So I think it's going to be a very non-trivial Hamiltonian if there's a AGB equation.
What you meant is that this lambda is not in the drift of the agents here?
No, I mean if...
because our principal doesn't have a state dynamics. They only have a control. Like our principal, let me show you the principal model. Yeah, they have an objective, but they don't have dynamics.
Okay. But then I don't know. Just a very stupid question. What happens if you try to write down the Hamiltonian, either if you're doing AGB or maximum principal? If you try to...
Yeah, actually, that was one of our future work. We were interested in basically, is it cut or am I cut? Can you hear me?
I think yes,
Okay.
we can hear you. I think it's him
Is it
probably.
cut? Okay, maybe I can wait a little bit. Yeah, what I was gonna say is that we were interested in maybe thinking or like a single level problem, this one. A little bit like a stochastic optimal control problem, a little bit extended, and maybe trying to write this AJB on this, but I'm not sure how it would work. It was a little bit future direction we wanted to do.
Mm-hmm.
Oh, I think it is. He's
Yes.
okay.
Thank you. Bye.
Yeah, I'm sorry, I lost my network.
Oh, yeah. So what I was saying is that actually one of our future direction we were thinking of doing is that this is a little bit like stochastic optimal control problem. It's a little bit more extended. And I was thinking like this can be maybe solved with AJB, but we didn't do anything yet. But what we are thinking, it should be fine. Yeah.
Okay, thank you. Yeah, thank you very much.
You're welcome.
Okay, thanks. There is another question in the chat. I partially answered while you were talking, but it's about can it be generalized to heterogeneous population?
Yeah, I think it should be, because what we are going to do is that for each population, we are going to have their own FBSDs. I get this actually question a lot in the talk, so maybe we should do it. So like what we are going to do is that we are going to have FBSDs for like each population. So we can do the same thing here, and each of them are going to affect probably the principal in the year costs. So the algorithm should work, and I think theory should work too, because we can write the FBSDs in the forward form, and we can even like write them as one big system. And I think from there the theory should follow similarly.
Okay, thank you.
Yeah.
All right. So if there are no further questions, well, thanks a lot everyone for attending, and thank you
you so
again, Gökçe,
much.
for the nice talk.